Alright, welcome back. We're going to look at the swinging pendulum and see how mathematically we can set it up in such a way that it's pretty much identical to the mass moving up and down on a spring. And so let's consider I have a mass on a length of string of length L. And there's some maximum angle theta through which it swings on either side, ignoring air resistance, frictional losses, even torsion in the string, meaning the twisting of it, that whatever distance I pull the pendulum back up to here, it's going to swing all the way back up to the other side and keep moving back and forth and back and forth and back and forth. And we had discussed in class about a week ago, like, how do we set this up? This is actually moving on these little circular arcs. And these arcs they have a length, and we can consider this circular. We can even invoke polar coordinates if we want. But there's actually, if we consider short motions, meaning the small angle approximation. So we consider small angle oscillations, or actually specifically small angle amplitude would be a better way to put it. Actually, I don't want to change the color yet. The small angle approximation summary sine of theta is just approximately theta. And then the cosine of theta is approximately 1. That's for very small values. And we can consider looking at it over here. If I graph, here's my sine of something. We can call this, sure, we can call it x. So this is y equals, not y, blah. X equals sine of t, and that would be pi, and that would be 2 pi. And then I can do in blue, and I always want to make sure that everything is lining up properly. The blue is x equals cosine of t. So this would be pi over 2, and this would be 3 pi over 2. And so in the small angle region, small angle would really be just like small t here. That's the small angle region. We can zoom in on the small region, and we see that for here, sine of some small value, I mean this is going to be t, so sine is approximately just t, so sine of 0 is 0 in a sense, because everything stays close. And then this is sine, or not sine, but this is cosine of 0 equals 1. So everything, as the argument of the trig function goes to 0, cosine goes to 1, sine goes to 0. So that's just a refresher of our small angle approximation that we are using. So considering a small amplitude for this pendulum, let's see, I'm going to use something like, what color? A thicker purple. If this is a small amplitude, then I can approximate this as a series of, as two right triangles. And in a sense, my mass is not moving in an arc like this, but the mass is actually just moving back and forth on some x-axis. I can call this x equals 0, and this is, I'm down below my point, and this is x, the plus x, and this is minus x. So in the small angle, instead of moving on an arc back and forth, my pendulum is just oscillating back and forth horizontally. It's not actually doing it, but we're doing this just so we can simplify the calculations for this and see that mathematically, again, what we call the small angle amplitude, the small angle pendulum, this is no different than the mass going up and down on a spring. So let's look at a free body diagram of our mass in this way. If I have my mass, some mass m, the weight is always acting down on it, the mg. And there's going to be some tension pulling back up in the string that's holding it. But if we consider a small angle approximation, and this is theta, and this is also theta with respect to some vertical line that we draw where the mass is at equilibrium. I can call this t sine of theta, and this is t cosine of theta. Now remember, if I define my triangle here, I'm just going to call this, ty, and this is tx. That's theta, my hypotenuse is t. So the opposite angle, tx over t, is equal to sine of theta, hence the t sine theta here. And the adjacent angle, or adjacent side, ty over t, is equal to cosine of theta, hence the t cosine theta over here. So you have to be aware of how you set up your triangles. And keep track, again, of what are your adjacent sides and your opposite sides relative to the angle in question. If we were looking at this angle instead, then things get flipped, but we're looking at the other angle. So again, the small angle, we're assuming that theta is really, really tiny, such that we can make an approximation. Sine of theta is approximately theta. So now that I've set this up, I know that as the mass swings, this is what we call a restoring force. Because if the mass goes off to the negative side, then that t sine theta is going to pull it back to the center. And then if the mass goes off to the positive side, over here, that t sine theta is going to point the other way. So t sine theta always acts to pull the mass back to equilibrium. And that's the center. This whole theta point, it's not constant. In a sense, what we're really looking at, theta is a function of time, in a sense. So the theta is always changing. But we're redefining this using some x-axis where our mass is moving back and forth rather than an arc in a straight line. So now that that is the restoring force, we've established that, I can set this up. I know that t cosine theta is equal, in a sense, to mg pretty much at all points, but if theta is always small, then I can say that the tension is approximately mg. And then I have this other relationship that's always changing, but I can consider that whatever my x is, and again, x is just like theta, is a function of time. That's x, that's L, that's theta. So sine of theta is equal to x over L, but if it's small, then I can say just theta is approximately equal to x over L. So now my restoring force, T sine theta, and I've established that T is approximately mg, and I'm going to put a minus sign because I know it's always acting opposite of the x. So we have minus mg. That's the t part. And then the sine theta is approximately x over L. So that's the sine theta part. So this is approximately t here, and this is approximately theta. And again, we see that from the narrow triangle here, and then also that the t is going, or the t sine theta, that restoring force, always points opposite of the displacement from the origin. So if the displacement is negative, let's go back up to my axis, if the displacement is negative with respect to this 0, then the t sine theta points back in. Whereas if the displacement is positive, the t sine theta points in the negative direction. So it's a restoring force, just like a spring. This is always equal to the net force on the mass. I'm assuming that the vertical force really isn't changing, and that's what I showed here. And F net, of course, is equal to the mass of an object times its acceleration. So now let's clean this up. I have an expression such that F, or actually, let's just rewrite it as ma equals minus mg times x over L. And remember that this is a function of time, and this is also a function of time. So I can clean this up even further. Notice that the m's cancel. That's interesting. So now I have this a equals minus g over L times x. And I can change this further. I can say that d squared x over dt squared is minus g over L times x. And x, again, of course, is a function of time. So now I have a function such that when I take its second derivative, I get a minus sign times some constant. Well, we saw in the previous video that the solution for this is something like a sine function. So I can say that this is the same as setting up d squared x dt squared is minus omega squared, and this time x of t. That's pretty powerful, because it looks just like the same equation we did for the spring. So the solution for this, one possible solution, again, the solution to a differential equation is a function. X as a function of time equals some sine of omega t, and omega in this case is, I can equate these two pieces here, so omega is the square root of g over L. Now, consequences of this. These are huge consequences. The only thing that a small amplitude pendulum depends on it for its frequency is the gravitational acceleration, the local gravitational acceleration, and the length of the string. So a longer string means a lower frequency. The whole thing oscillates slower. A stronger G means a higher frequency. And we can't really change G, so we can always change the length of a pendulum. So shorter pendula will oscillate faster. Longer pendula will oscillate slower. The only thing that matters is the length. The mass doesn't matter, because it canceled out over here. So let me just label these pieces for us. this is, again, the equation of motion. And the same thing, that's also it, and that's also equation of motion. That's it as well. This is it. This thing here, again, is a position function. And then working up here, this is the free body diagram of our system. So using a free body diagram and then some assumptions to make this easier, this only works for the small angle pendulum, we get a most important result. And the mathematics is exactly the same as the oscillating mass on a spring.